Okay, can you see that it is being recorded?
Yes, we can see.
Yes, sir.
Okay. Okay, so this is the first lecture for quantum mechanics course, and we will start with references. So the books that I will be using are kind of listed here. Physics of Atoms and Molecules by Bransden and Georgian is the main book, really. It's a big book. It's about 1,000 pages or something, and but we will kind of not use everything of that. But yeah, but probably 60% of that will be used. But not like, they talk about a lot of things, give several examples. We will not do all that. There's another nice book on atomic physics by Christopher Foot, which is also good. There is a theoretical atomic physics by Friedrich, and there's a molecular quantum mechanics book by Atkins and Friedman. And Atkins and Friedman is a good book, although I would still say that Bransden and Georgian is probably the best, particularly for this course. And this course is again shared with Pinaki, and unlike the advanced atomic course, Pinaki will teach almost 50% of this course. There, like, he's supposed to teach one particular piece. So I'll essentially teach atomic and molecular physics part of the course, and Pinaki will teach atoms and light, cold atoms, collective effects, and so on. Okay. Teaching assistant is Tanaya Ray, and actually I haven't gotten in touch with her, but I'll drop her a line, and she'll have to kind of schedule interactive sessions at some point. But I think she has gone home, so from home she'll have to attempt these sessions. I hope it will be possible. Okay. If not, then you please let me know. We can try doing some arrangements. Okay. So
Yes, sir.
I have some plan about evaluation pattern for this course, and since I will be teaching only 50% of the total credits, Pinaki is going to teach remaining half of the course. In this 50%, like 40% of that would be home assignments, and then there will be 60% of it would be some mid-semester exam, which will be sometime between November 16th to 20th or something. We can try figuring out what would be the suitable time and date. Okay. So that is a rough structure of the course. And any questions about this? Pinaki will essentially take over after the mid-sem exam week. Okay, so he'll start teaching from November 21st onwards. I mean, okay, November 21st is probably Saturday, but not that way. But after that, okay. So we will stop wherever we reach before the mid-sem exam. Okay. Okay, good. So let's start with relativistic quantum mechanics, because this is something we would need when we will do atomic physics, for example. Okay, so relativistic quantum mechanics is a mixture of two successful theories. One is special relativity and the other is quantum mechanics. And both these theories developed around the turn of last century. All of us know that they are very successful. And what we will see that relativistic quantum mechanics is a successful combination of these two theories. Okay. Now, it is not always true that, like, you have two successful theories, you can successfully combine them. We have not been so lucky. For example, we haven't been able to combine quantum mechanics with general relativity, which is one of the notoriously difficult problems. And till date, we really don't know what is the correct form of what one would call a quantum gravity theory. Okay. Of course, everybody has their own favorite candidate for quantum gravity, but in reality, we really don't know much. So in this particular case, of course, we have succeeded in getting a good relativistic quantum mechanics. Okay. I would kind of follow a historical path. I have a feeling that you may have done some part of relativistic quantum mechanics in QM2. If not, please let me know.
Yeah, we did Dirac equation.
I see. And Klein-Gordon equation also?
I mean, we saw it. I mean, both the equations we only saw and did a couple of things,
Okay.
but not in detail. So,
Okay. Okay. So I think we will just go through that. Of course, we will not do those equations in great detail in the sense that uh, that we will look at only at those aspects which will be useful for atomic and molecular physics. So there are various other things that we could do which could be useful, say, for setting up quantum field theory and Klein-Gordon field theory and Dirac field theory and so on, which probably, or not probably, but in some sense will be done in QFT1 course, I would believe. Okay. Anyway, so I plan to take a bit of a historical path, so it is a bit amusing, I would think. If you find it boring, please let me know. We can change track there, this thing. But what we are going to do is to try to follow how relativistic quantum mechanics developed historically and try to understand as to why, for example, the Klein-Gordon equation is called Klein-Gordon equation and not anything else. Okay. Uh, Fine. So unlike non-relativistic quantum mechanics, where we study single particle mechanics of self in a self-consistent manner without being compelled to go over to say many body physics, relativistic quantum mechanics requires you to actually go to a more general setup called quantum field theory. And that is because there is no invariant notion of single particle mechanics in relativistic quantum systems. Okay, so therefore you cannot really say that you are actually studying only single particle system, although you do study single particle system many times, but interacting system typically has particle antiparticle creation, and therefore you may start off with a single particle system and you end up studying you know multi-particle system. But if you are looking at a single particle, total particle number would still be one, in the sense there'll be n plus one particle and n antiparticle, and so the total charge is still one. But uh, total number of particles is of course 2n plus one or something like that. Okay. Fine. So we will, this is about conventions. We will try to follow the conventions written here. I will try to keep track of H bar and C at least in the relativistic quantum mechanics part. And if I do not, then I will always fall back to convenient choice of H bar equals C equals 1. I will try to avoid doing that at least in RQM part. Once we get into atomic physics, maybe it will become too heavy to kind of carry all these variables, but let's see. Okay. We of course have x naught equals ct and x vector being x, y, z. P0 is e by c and p vector is just momenta. Okay. We choose a metric which is 1 minus 1 minus 1 minus 1. This is a favorite metric used in particle phenomenology. Particle theory typically uses the opposite one, but let's not get into that. Okay. Uh, we of course use Einstein summation convention. That means if you write A dot B, which is A mu B mu, then we have summed over mu. Okay. And A mu B mu is same as G mu nu times A mu B mu. Okay. That is a usual structure. Okay. So let's ask the question as to when do we need to study relativistic quantum mechanics? Okay, now it may appear like a kind of elementary question, but it is not as elementary as it appears to be. So of course, we know that if you are looking at everyday life objects, then we don't even need to study relativity. Non-relativistic classical mechanics is good enough. But there are situations when you are looking at particle velocities which are comparable to the speed of light, and that is the time when you need to study relativistic mechanics. Okay. although there is no clearly defined crossover between non-relativistic systems and relativistic systems, one can kind of roughly quantify this by looking at the relativistic dispersion relation, E squared equals P squared C squared plus M squared C to the 4, and say that whenever P times C is greater than or equal to MC squared, then you would say that the system is relativistic. Okay. In other words, kinetic energy of the particle is comparable to its rest mass. That is a kind of limit. Okay. So I just repeated the sentence here that we say the system is relativistic when PC is greater than or equal to MC squared. But the point is that, like, even if you are in a situation like this, you would still be studying special relativistic system, but to do classical physics. Okay, we still need to ask a question: under what circumstances would you want to do relativistic quantum mechanics? To determine that, we need to kind of ask a question as to what is the scale which defines or below which we need to use quantum mechanics. Okay, and in non-relativistic quantum mechanics, we know what is that scale. And that is what we call de Broglie wavelength. And whenever you look at this particular object, you say that if you are probing a system at a distance scale smaller than de Broglie wavelength, then in that case, you should necessarily use quantum mechanical description of the system. Okay, so de Broglie wavelength is of course given by h upon p, where p is the momentum of the particle. And if the physics is probed at lower scale, then the description has to be exclusively quantum mechanical, and no classical description would make sense. Okay. The problem with this particular length scale for relativistic mechanics is that if you are looking at, say, massive relativistic particle, for example, electron moving at very high velocity and stuff like that, okay, then what happens is that, like, it seems to give you an impression that that as the energy goes up, the quantum regime seems to recede from and therefore, as you go to a smaller and smaller scale, as you start probing smaller and smaller scale, you find that the corresponding quantum scale is even smaller than what you are probing. Okay, so it seems like you will never reach you will never need relativistic quantum mechanics. Okay, so just to understand that, you see that, like, when the momentum starts going up, you think, then the wavelength starts becoming very small. And if the wavelength is very small, then you need to probe much shorter distances. But to probe at things at much shorter distances, you need higher energy, and that would again push the momentum up, and the system again goes to the corresponding scale again starts dropping down. Okay, so that is the kind of puzzle that one encounters with the de Broglie wavelength. However, what happens is that, like, that is not the only scale available in the system. Besides that, we also have another scale which is called the Compton wavelength, which is an intrinsic wavelength corresponding to every particle. And the Compton wavelength is defined as h bar upon m times c. Okay, so this is the scale that one is looking at. And it is the Compton wavelength which decides the crossover to quantum mechanical regime in the relativistic situation. Okay, so notice that the mass that is used here is the rest mass of the particle. So it is not it's not the moving mass, because if you are doing the moving mass, then you are again in the same situation that you were in case of the de Broglie wavelength. But that's not what happens in this particular case, because Compton wavelength is defined for a particle with its rest mass. Okay. So anytime you are probing physics at length scale smaller than h bar by mc, then you necessarily need quantum mechanical description. And if the length scales are that small, you can kind of try to do the calculation. You'll find that the system is typically in the relativistic regime. Okay. In fact, what we will see is that the Compton wavelength appears in an interesting way whenever you write down relativistic quantum mechanics problems. Okay, and this is one of the reasons why at least in the relativistic quantum mechanics part, I would like to keep H bar and C explicitly for us to actually appreciate how quantum wavelength appears in the relativistic equations. Okay, so now there is a interesting question that one could ask, namely why non-relativistic quantum mechanics first and relativistic quantum mechanics later in the historical development of this subject. And the reason why I'm asking this question is that, like, the time when quantum mechanics was developing, special relativity was already a well-established theory. There was no doubt about whether special relativity is making sense or not, or nothing like that. People knew it very well that that is the thing. Newtonian mechanics is a kind of a small wavelength, small velocity limit of the system. And therefore, if you want to write down any equation, it would be something which should be, I mean, it would be great if it is consistent with special relativity, because then it would automatically be consistent with non-relativistic or Newtonian mechanics. So therefore, it would have been a natural question, why not try to write down quantum mechanics directly in a relativistic formulation? Okay, and as I said, there's an interesting history behind this, but one line summary of why this did not happen is that the initial attempt of writing relativistic quantum mechanics failed, and non-relativistic quantum mechanics succeeded in explaining a variety of experimental phenomena. Okay, of course, you know, this is not to say that non-relativistic, not to say that relativistic quantum mechanics was actually wrong. It was right, but it was being applied for a different kind of particle. That is the place where the failure was, as we will see later, uh, as to why this particular program was actually abandoned. Okay, so so of course, after kind of abandoning this idea of getting relativistic quantum mechanics and kind of falling back on non-relativistic setup and getting reasonably good agreement with experimental data, people reattempted to get relativistic quantum mechanics, and in the second attempt, of course, people succeeded. Okay. So let us look at what is called the Schrodinger-Klein-Gordon equation. Now, of course, nobody calls it a Schrodinger-Klein-Gordon equation. So I need to qualify why I am calling it a Schrodinger-Klein-Gordon equation. It's of course called only Klein-Gordon, and that's what we'll call later also. Okay. So to understand this, we'll basically start with the relativistic dispersion relation, which was the same as E squared equals P squared C squared plus M squared C to the 4, which of course has two solutions, E equals plus or minus square root of that quantity. Okay, P squared C squared plus M squared C to the 4. And the positive energy solution is easy to understand because, you know, one knows about particles. One knows that those particles have positive definite masses, positive energy, and so on. And but the negative energy solution seems to indicate instability, because that would have indicated that there is no lower bound on the energy, and in that case, you know, you could just keep going to lower and lower energy by emitting particles of positive energy. Okay, and it seems like, you know, system could become unstable simply because negative energy states, arbitrarily negative energy states could just exist. Okay. Now, of course, this sign ambiguity is fundamental in understanding the relativistic theory, and it took some time for people to actually understand what this sign ambiguity really corresponded to. Okay. And the reason why it took some time was because historically, when people were studying the relativistic system, people had not observed antiparticles. Okay, so therefore, it was kind of a leap of faith, at least when multiple attempts to avoid that negative sign failed. Dirac at some point basically predicted that there must be negative energy objects which should have opposite charge, and he tried to call that hole, and later on it was called positron, for example. But it required some imagination to come up with the concept of antiparticles, which did not exist at that time. But now we know that positive and negative energy solutions correspond to particles and antiparticles in relativistic theory.
Sir, like for example, in classical relativistic mechanics, we don't consider this negative energy, right? Because that does not sound visible.
That is right.
But yeah, but what? Why didn't they just rule it out in quantum relative
If you
RQM?
we will do that stuff soon.
Okay.
We'll ask this question.
Sir,
Yeah.
sir, is this, I mean, negative energy of arbitrary negative consistent with statistical mechanics? Because then everything will go to that level actually.
Yeah. So that
In
is
the Boltzmann factor.
that was a puzzle, right? That is what people thought, that like it would basically kind of go to arbitrarily negative energy, and in that case, by just emitting particle system could go to negative, arbitrarily negative energy. You will understand that it doesn't happen this way, right? Even to produce an antiparticle, you need to provide positive energy, really. Okay.
Sir, isn't it related to the fact that even to produce simple Dirac delta normalizable state, we need to keep the limits of the Fourier transform to minus infinity to infinity?
Exactly. That
if
is.
we go to energy.
Yeah, exactly. So that's what we will do. If you hold,
okay.
if you hold on, we will see that. Okay. So another feature that we encounter in relativistic formulation is the notion of spin, and this notion appears naturally in the relativistic formulation as against in the non-relativistic formulation, where spin was put in by hand. And it was put in by hand simply because certain properties that electrons had was not possible to explain by using just scalar wave functions, and Pauli proposed that it should carry some additional intrinsic quantum number called spin. Okay, and but in the relativistic setup, this notion comes about naturally. Of course, if you are trying to look at Klein-Gordon equation, you wouldn't see it because it describes a particle with spin 0. But nevertheless, the concept of spin appears naturally in relativistic quantum mechanics, and it could allow spin value of spin to be equal to 0 also. Okay. The thing is that, like in although it appears naturally, relativistic quantum mechanics doesn't know how to restrict these numbers. Okay, what should be the allowed spin value? Okay, so only thing that is allowed, I mean that is kind of dictated by the symmetry of the theory, say in 3+1 dimensions, is that the spins could be half integral. Okay, so it can be 0, half, 1, 3/2, and so on. But it cannot tell you that the value of the spin should stop at, say, spin 2 or spin 5 or any other number. Okay, it can be arbitrary spin. So in that sense, there is no clear way of saying that why higher spin particles are not so easily observed, or why the spin should not be more than a particular value. Okay, there is no way a relativistic quantum mechanics could dictate that. Okay, of course, for every particle with different kinds of spin, we'll have to write down different relativistic equations. So you write down one equation, it cannot give you a particle with arbitrary spin. So in that sense, you'll have to kind of write separate equation for every particle carrying a different kind of spin. Okay, so but what we could do is we could start off with particle with no spin. Okay, spin 0 particle, and Schrodinger Klein-Gordon equation is a ideal setup for describing relativistic particle with no spin. Okay, so to proceed further, we would basically follow the usual technique that we learned in non-relativistic quantum mechanics. We replace E by IH bar del del T and P by minus IH bar nabla. Okay, and substitute that in the dispersion relation, and that gives you this equation, which I have called Schrodinger Klein-Gordon equation. And the reason I'm calling it Schrodinger Klein-Gordon equation was because Schrodinger in fact wrote this equation to solve the Coulomb problem to determine hydrogen atom spectrum. Okay, and this was done much before Klein-Gordon even looked at or wrote down this equation. Okay, and not only that he wrote down this problem, I mean, this is a free particle equation, but he replaced the this equation by Coulomb problem. It added the Coulomb potential and so on. And he studied that system, and he could determine the spectrum of the hydrogen atom, but he did not agree with those predictions and the experimental data. Okay, and that was the reason why. Yes.
So if we try to invoke a potential, then how can we do this in this format of an equation?
How can you do what?
I mean, if we try to insert a potential kind of thing, how
Yeah.
can we do that in this format?
Oh, because the way to do that is basically you replace the, I mean, suppose I try to write it in a covariant form, okay, for simplicity, okay. Then second derivative with respect to time and secondary derivative with respect to space can be written as just del mu kind of thing, okay. You replace del mu by del mu minus a mu, right, and convert that ordinary, convert partial derivative into covariant derivative, right?
Okay.
Then in the covariant derivative, the A0 part of the gauge field is like a Coulomb potential, and A vector is the vector potential which should be responsible for magnetic field effects and so on. Okay.
Okay.
Okay. Fine. So he found that his result did not agree with Bohr's predictions and with the experimental data, and therefore he just abandoned the program, and he decided to take non-relativistic limit of his equation, and that non-relativistic limit of that equation is what we call the Schrodinger equation now. Okay, and then he solved the non-relativistic Coulomb problem and found that the spectrum matches with the experiment to great accuracy. Okay, we will visit this problem in this course, and we will see that, like, in fact, the reason why he gets the answer right in the non-relativistic limit is because he makes, well, he doesn't make, but like in the process of doing taking the non-relativistic limit, one makes kind of one more mistake, and in the effect, you kind of get the answer right. Okay. So there is already one problem in the relativistic limit, but in the non-relativistic limit, there is one more problem gets introduced, and both of them cancel each other to give you a right answer. But we of course know how to solve the hydrogen atom problem, and it is not to be solved using Klein-Gordon type equation, or what I call Schrodinger-Klein-Gordon equation. But the right kind of problem would require a Dirac equation to be used to solve that problem. So we will of course use Dirac equation also. So we will kind of try to solve hydrogen atom problem in two different ways. Okay, fine. So of course Klein and Gordon knew about this attempt. Schrodinger never wrote up this calculation. He never wrote this relativistic equation of his, but people knew about it, including Klein and Gordon. And in spite of knowing that, and in spite of knowing that it does not work for hydrogen atom, they persisted with the equation, and they just said that, like, let's study this equation in its in its present form and see what it corresponds to. And they basically wrote down that equation, and which is what we call Klein-Gordon equation now. Okay, and now if you kind of look at this equation 2, they are just trying to write that in a covariant form by multiplying and dividing on the left hand side by c squared, and then ct is being written as x0 and so on. You can write down that equation in this particular form, and notice that mc upon h bar is the inverse Compton wavelength that appears in this equation. Okay, so a natural scale in the relativistic equation is the Compton wavelength and not the de Broglie wavelength. Okay. Okay, so here's the equation again. The simplest solution to this equation is, of course, a plane wave solution, and you can write down it in this particular form: exponential minus ip dot x upon h bar, where p squared is equal to m squared c squared. Under that condition, you can show that this equation would be satisfied by this plane wave. Okay. Now, the difference between this equation and Schrodinger equation, the Schrodinger equation is what we call a parabolic equation. Parabolic equation is the equation which is first order in one variable and second order in another variable, typical partial differential equation. Whereas Klein-Gordon equation is more like a hyperbolic type, which is second order in both variables, but they have a relative sign. Okay, that relative sign comes because time coordinate has a different behavior compared to space, and that is why it is hyperbolic type. If you did not have something like that, for example, equation of say a Laplace equation or some such thing, those are the kind of equations which are called elliptic type. Okay, so elliptic type equations are typically harder to solve. Hyperbolic type equations typically have good initial data, and you can evolve those equations in much better way than elliptic equations. And parabolic equations kind of fall somewhere in between. Okay, so so we know that Schrodinger equation is first order in time, whereas Klein-Gordon is second order in time. Okay, so and this particular fact reflects onto the conserved current that one could derive from Klein-Gordon equation. This is something we have studied even in non-relativistic quantum mechanics when we studied Schrodinger equation, that there is a continuity equation that is satisfied by Schrodinger wave function. And you could do the same thing with Klein-Gordon equation also. You can multiply the Klein-Gordon equation by psi star and subtract from it a conjugated equation multiplied by psi, and you get something like this. Okay, and since the mass term is kind of does not contain derivative, when you subtract terms, it just drops out. Okay, so you get an equation of this type. But you can show that this equation can be written as total derivative on both sides. Okay, so this can be shown to be del t of a quantity like that. I is power upon 2 mc square is a kind of a normalization. You don't see a mass term here. I'll tell you why I'm trying to do this. The reason for doing this is that the piece on the right hand side here, not right hand side, but the current piece would have the same normalization that you would encounter when you write down Schrodinger equation. Okay, so to get that form, all you have to do is to just multiply this entire stuff by mc squared. Sorry, divide the entire stuff by mc squared and write down the expression. So since the right hand side is 0, you could happily done that. Okay. So you can think of this equation as a continuity equation for the Klein-Gordon equation, and in that case, the term on which del t is acting can be interpreted as the charge density, and the nabla is acting on the current density. Okay, so that is the kind of form that you would encounter. And current conservation equation would tell you that the charge associated with this rho is conserved. Okay. Now let's go back to Schrodinger equation. And in case of Schrodinger equation, also you have a continuity equation, but rho in that case is mod psi squared. And that is because the equation that you had at this level was first order in time. And because it was first order in time, you could just pull that out and you get a psi star psi piece sitting around. Okay, but since Klein-Gordon has a second derivative with respect to time, your rho is written in terms of derivatives of psi and psi star, and that's why it is a object which is different from what you would see in the Schrodinger equation. Of course, we know that rho equals mod psi square has a nice interpretation as a probability density, and the charge conservation leads to conservation of probability. And this is the Max Born interpretation of the non-relativistic quantum systems. Okay, for the Klein-Gordon equation, the situation is not as easy because rho, if you look at this, is real. Okay, you can check that because it is once it's a derivative of psi, once it's a derivative of psi star, but then because of the minus sign and I, you can see that this quantity is actually real. Okay, but it is not necessarily positive. And if it is not necessarily positive, then you cannot give any probabilistic interpretation to this object. Okay, and therefore the situation here is a little different from the way you would have encountered used in, say, Schrodinger equation in non-relativistic quantum mechanics. Okay, so we can write down the same current where zeroth component is rho and vector component is the quantity written up here. And you can write down that in a covariant form like that. And the covariant form of the conservation law is just del mu J equals 0. Okay, so the thing is that, like in the non-relativistic physics, the time is absolute, and therefore rho is independent of time. Okay, and it is good enough because if it is independent of time, it kind of ensures the current conservation automatically. Okay, but in relativity, time is not absolute. Time itself is relative, and in that case, rho is not independent of a choice of frame, and that is just as well, because if you look at an expression like this, and if you want to compute the charge corresponding charge associated with whatever rho you are looking at, and if you do this integral, then this integral value of this integral would depend on which frame, in which frame you are doing the computation, because in one frame you will get some answer, in another frame in which the object is moving, there will be a length contraction effect, and because of the length contraction effect, the corresponding volume would appear to be smaller than the volume that a stationary observer would have seen with respect to observer for which the charge was at rest. Okay, so clearly that would contradict the conservation law, and so therefore it is clear that rho cannot be independent of frame. Okay, and so what happens is that, like that rho contains a factor which is precisely the factor which compensates for the length contraction factor for the volume when you volume element in the integration, such that rho times d cube x is independent of Lorentz transformation. And once it is independent of Lorentz transformation, then every frame it will give you the same answer. Okay, so that is the reason why rho is not independent of frames in relativistic problem, but it is time independent and therefore independent of frame in non-relativistic physics. Okay, so to understand the relation a little better, let's consider a plane wave kind of in a stationary state with e to the I minus IHT kind of IET type of wave function. Okay, and so not exactly plane wave, it may not be plane wave in space, but at least in time. And you substitute that into the rho, and you would find that rho would be E upon mc squared times I star psi. Okay, and this form is pretty close to what you would have seen in non-relativistic case, except for the factor E upon mc squared. And as I was just explaining, that you need this factor E upon mc squared to compensate for the length contraction effect that you would have seen in the relativistic mechanics. Okay, fine. Okay, so this is what I was just saying, that the simple explanation of this is that the Lorentz transformation effect would be kind of taken care of by E by mc squared factor in the rho. Okay. Oh, sorry, there is a typo. Okay, but anyway, so I can explain. I'll correct that equation in a moment. Okay, maybe I won't do it online. So in the non-relativistic case, the number density and the charge density are equal. So rho n and rho q, not rho minus q, but rho underscore q actually. If you can give me a minute, I'll just do it. Oh, well, maybe I'll do it later. Sorry, it's taking longer to search that object. Anyway, so the number density and charge density are equal in the relativistic case, simply because the particle number and charge is a kind of same quantity. But that's not true in the relativistic situation, and that is simply because you may have a charge value to be some number, say 3, but you may have 4 particles and 1 antiparticle, or n plus 3 particles and n antiparticle, and so total number of particles could be much larger than the total amount of charge that you actually are measuring. Okay, so and this happens because of pair creation that is allowed in relativistic systems and not allowed in non-relativistic systems. Okay. Okay. So what happens in this particular case is that the rho that we have computed here, where you substitute mu equals 0, is actually measuring the charge density. Okay, because it is the charge carried by size minus the charge carried by size stars. So it is basically measuring the charge density and not measuring the number of particles. Okay, so that is why rho here is rho q and not rho n. Okay. But another advantage of this is that since charge can have either sign, it can be positive or negative depending upon which kind of particles are more in the collection that you are looking at. It naturally gives an explanation as to why rho is not necessarily positive definite. Okay, and so what we find is that for positively charged particles, that means when the particles have positive charge, that's what I mean by positively charged particle. If you have E is greater than 0, then the corresponding particles would have rho positive. And when E is less than 0, then that would correspond to antiparticles, and for which rho will be less than 0. Okay? Is it fine? Hello? I hope people are around.
Yes, sir.
Okay, thank you. No, I thought otherwise, I got disconnected and kept talking about something. Okay. Okay, so so as I said, that when the relativistic mechanics was being studied, the antiparticles were not discovered, and therefore it was kind of difficult to come to this conclusion that rho negative would correspond to a new kind of particles that are not seen so far. So one could ask this question, which is something we discussed a few minutes ago, as to why can't we just truncate the spectrum and just look at positive energy states? Okay, and the answer to that is that if you look at the Fourier transform of any function, that goes from minus infinity to plus infinity. Okay, and this is how the expression would look like. And if you try to restrict this integral from 0 to infinity, this is an energy integral. And if you say, okay, I don't want negative energy states, you can just ask, how do I restrict this integral from 0 to infinity? And you would find that this restricted integral will never give you this profile for phi of t for any choice of phi tilde. Okay, so this is something which kind of follows quite trivially from the Fourier transform. And as Aman was saying some time ago, that it trivially follows if you choose phi of t to be delta function. And in that case, you cannot even truncate this integral from 0 to infinity, because if you do that, you will never be able to reproduce delta function by doing the integral of this kind. Okay.
So, but we could give the same argument in non-relativistic quantum mechanics, right?
Yes.
Like if we in non-relativistic quantum mechanics, if we want to write a function and write its Fourier transform, then we'll have to integrate it from minus infinity to infinity in the energy spectrum.
That is right.
So, but why don't we say this in like non-relativistic quantum mechanics, that like E should have negative values as well.
Yeah. The reason why in the non-relativistic quantum mechanics you don't encounter this is because most of the systems have, I mean, like suppose you turn on a potential, okay, the potential naturally has a bounded spectrum, right? And
Okay.
if you are taking all the states correspond in your quantum mechanics problem, then you should be able to express delta function in terms of those complete set of states, right? So you are not forced upon, there is nothing which forces you to use negative energy states because they just don't occur in the problem.
So the problem here, isn't it that the kinetic energy is being negative?
No, kinetic energy is not negative.
Isn't this totally the kinetic part that is becoming negative? Because we haven't considered any potential yet.
Yeah.
In non-relativistic quantum mechanics, the only time we encounter negative energy is when we have a potential going to minus infinity or something like that.
What I meant was that, like, suppose you look at free particle in quantum mechanics. That is the equation which says E is equal to p squared, right? Up
Yeah.
to normalization, like up to 1 over 2 m factor and so on. And E equals p squared is manifestly positive definite. Okay.
Yes.
So therefore entire spectrum in complete set of states are written in terms of positive definite energy states.
Yeah, and that is true for non-relativistic for the kinetic part term.
Yes.
Yeah, and here the issue is that we are writing something like E square equals some p square plus mc square,
And
m square c4.
that is still positive. The square root has a sign.
And square root has a like mathematical inconsistency in sign or something which needs to be interpreted.
Exactly.
And that is truly an artifact of relativistic quantum mechanics, right?
Exactly. I mean, in non-relativistic quantum mechanics, complete set of states are all positive energy states.
Yeah.
They're not forced upon using negative energy states at all. So if you have a complete set of states, then any function is representable in terms of those.
Also, I wanted to ask, like, so far we haven't talked about it, and even in the other course, I couldn't grasp what the meaning of wave function now is.
Wave function?
What is the meaning of wave function now? In the sense that in non-relativistic quantum mechanics, we stipulated some things, like one of them was conservation of probability.
Yeah.
But even aside that, we had some normal postulates by von Neumann, like it comes from a Hilbert space.
Yeah.
Applying operators will give eigenvalues and things like that.
That's right.
So it sort of gave a picture of what the wave function represents.
Yeah.
But
Okay.
right now, I'm not sure what in the Klein-Gordon equation, what is that psi actually representing? Like, what do we use it for?
Well, psi definitely describes the wave, right, corresponding to a particle. I mean, it still corresponds to a probability amplitude for a particle to be found at some place. Okay. So that is the reason why I was trying to tell you, trying to do this thing, that if you take a limit, you know, if you look at a plane wave in time, okay, then you still have an interpretation in terms of kind of a probability amplitude, okay, and in that case, psi is actually a probability amplitude for a particle, Klein-Gordon particle, okay.
I see. So are we still keeping the notion of operators coming from Hilbert spaces and all those things?
Everything follows. In fact, when you will do quantum field theory, you will see that all that will be written in terms of operators acting on Hilbert spaces and so on. But the thing is that, like, you are essentially forced to use quantum field theoretic notions and not really quantum mechanical notions, simply because there is no simple particle number conservation rule that you could use here. Okay. This is something you could do in non-relativistic quantum mechanics, because if you are studying one particle system, you are studying one particle system all the time. If you are studying 5 particles in some potential, then you are studying 5 particles. It never becomes 7 or 8 or 4 or something. Okay. This is something that is a special thing for a relativistic system, which tells you that the number of particles is not an invariant notion. And that is the reason why quantum field theory, in fact.
Sir,
Yes.
so I have a question. When we take non-relativistic limit, we'll take the non-relativistic limit of the theory or the equation of motion that comes. I mean, I don't see the C factors going on in, and I mean, I don't see the non-relativistic limit going to Schrodinger equation.
You don't see means?
I mean, it's not apparent. If you take C to infinity
Yeah.
of the Klein-Gordon equation,
Well, you don't take C to infinity. You actually say that the mass is much larger than the momentum, and you pull out the mass from the dispersion relation, and then
yeah. So
then you
okay,
actually that is how
so
you.
it's starting from the dispersion relation only.
Yes.
So we don't take the limit of equation itself.
Well, I don't know what you mean by limit of equation. Equation is come out. I mean, equation has been written by looking at the dispersion relation, right?
Yes.
So we basically follow that line.
Okay.
So the Fourier transform that you did, what are we doing that there?
Which Fourier transform this? Just hold on, huh? This one?
Yes, this one.
Yeah.
What are you doing there?
Yeah, no, I was just trying to say that, like, suppose I have a function, it's a function of some variable, say t. It doesn't have to be t, it could have been anything else, actually. And if I want to describe that in terms of its Fourier modes, okay, the reason why I use t is because I want to use energy integral in the Fourier space. Then this entire function is described in terms of phi tilde e only by integrating over energies going from -infinity to plus infinity. Okay.
Okay. Yeah, but how is it related to quantum mechanics? Because in non-relativistic quantum mechanics, we had this Fourier transforming x basis to p basis
Yeah.
kind of a thing. So, is
Yeah.
there a similar thing here for E?
X basis to p basis Fourier transform still makes sense because you allow plus minus x's values, plus minus p values, right?
Yeah.
So you do a similar transform and p goes from -infinity to plus infinity, which is not a problem. But p going from -infinity to plus infinity, p squared always is positive. Okay.
Yeah. Yeah.
So that's why you don't encounter this problem in non-relativistic case. But here you do simply because you have a second order in time derivative.
No, I was wondering what is this phi t? Means what is phi t? Phi t? Like, is it a wave function? It is not a wave function.
It doesn't matter. It could be any function. You choose any function, and you can ask a question: can I represent that in terms of a function? In terms of a function of E. Okay, that description is done in a Fourier space, right? And then you ask a question: can I restrict E variable from 0 to infinity? And the answer is no.
Okay.
Okay. It has nothing to do with any wave function or something. Any function, it doesn't matter what you look at.
Sir, I'm not too sure about the argument that's being made here. I mean, I don't see why this is a justification for why energy, why we have to take a negative energy states. Because this is just a mathematical convenience, right? Even in time when we take a Fourier transform, we don't really demand that at t, like at negative times, we had something.
What?
Or do we do that? Like,
We do that, yeah. In fact, like, when you do quantum field theory, you will also see that, like, if you have to really restrict yourself to only positive energy states, then you, in fact, add a heaviside theta function to do the computation. And then you will have to do some extra work to show that, like, the expression can be made Lorentz invariant by adding another term which cancels the Heaviside theta function factor. But otherwise, yeah, you do it this way only.
No, I'm saying that this is simply a mathematical tool, right? Applying a Fourier transform on a function.
Yes.
Just because, like, suppose I stipulate that I am not allowing negative energy states,
Yeah.
negative energy values.
Yeah.
But still, I can do a Fourier transform for functions and for mathematical simplicity evaluate phi of t, even though I might not want to make physical sense of it.
No, but you may not be able to describe the function in complete form.
Not even mathematically, you're saying?
Not even mathematically, yeah.
Okay.
So it's like, I give you an arbitrary function and I tell you that like you use only cosine transform to describe that. Okay. If your function is even function, cosine transform will give you the description completely. But if your function contains odd terms also, then cosine transform will be completely, and it will be impossible for cosine transform to pick up those terms. You need a sine piece to get it. Okay. So it's not just a mathematical statement. This, I mean, if you have a function which contains arbitrary polynomial pieces, simple polynomial pieces, you don't even have to take complicated function. Okay, you have something like phi of t is equal to 1 plus t squared plus t cube. Okay, you cannot do a cosine transform to get the answer. You cannot do a sine transform to get the answer. You need both of them to get the answer. Okay, so cosine transform is like saying that you are looking at only the positive energy sector of it, because cosine is even for positive and negative energy. So you can just look at positive energy part of it. It won't work. Okay.
Yeah. One thing I can understand from this, I'm not sure whether I'm understanding it right or not, that if we ignore the negative part, we'll lose the completeness property of the Hilbert space and things like that.
Completeness property is property of phi of t. Yeah. Not
Yeah.
if. Yeah, exactly. That's what is the statement.
Okay. All right.
Okay. So yeah. So as I was saying that like Klein-Gordon equation describes a charged scalar particle, for example, something like charged pions is, of course, pions are not elementary particles, but nevertheless, effective description of pions would be given by, say, a Klein-Gordon equation. Okay. The reason why I say charged particle, because remember we had a Klein-Gordon equation written as psi star and psi. But if the psi was real, okay, then in that case it would describe a neutral pion. Okay. So not just pi plus pi minus, but there exists a particle called pi 0, which would be described by psi, which would be real. Okay. Fine. So what we want to do now is that we could try to set up Klein-Gordon equation in a form where you can isolate particle degrees of freedom from antiparticle degrees of freedom. So we would want to write down this equation in such a way that you could just look at one piece and say that like this piece describes particle degrees of freedom. And then there's another piece which would describe antiparticle degrees of freedom. Okay. If you do this kind of thing, it has the additional advantage that the equation that you would write down is effectively first order in terms of derivatives with respect to time. Okay, so this form of equation is pretty much like the way you would write down, say, the Schrodinger equation. Okay, but of course the system is still relativistic. Schrodinger equation is a non-relativistic equation. So what we are trying to do now is basically try to set up equations in such a way that we could write down the equation in first order in time derivative. Okay, and we would kind of get the particles and antiparticle system separate. Okay, fine. So I think I'll kind of stop at this point, basically by giving a description of what is the set of variables that we are going to use, and we will use these variables tomorrow. Not tomorrow. Do I have a class tomorrow? I think so. No. I have class on Thursday, right? Hello?
Yeah, it's on Thursday, 11 o'clock.
Yeah, it's on Thursday, right? Yeah. So what we are going to do in the next class is to do the following thing: define two-way functions. Define eta, which is half times psi plus I h bar upon mc squared times del psi by del t, and define chi, which is half psi minus I h bar by mc squared times del psi by del t. Okay, and what we want to do is to look at these two objects, these two wave functions, and try to see what we could do with these. Now, one straightforward thing that you could check is the following: that if you substitute psi as a plane wave kind of thing that we were looking at some time ago, like this, okay, then you will see that, like, if you substitute this psi in this equation, then del psi by del t would give you a factor of E in the numerator, and IH bar would just cancel out. And if E is equal to mc squared, okay, then in that case, chi would just vanish, okay, because psi minus psi kind of expression, because E by mc squared is just 1, okay. And in that case, eta is the function that would survive, and chi would vanish, okay. And E is equal to mc squared corresponds to positive energy object, and therefore we would say that eta is like a particle degree of freedom, okay. And when E is equal to minus mc squared, in that case, this object, the object which is called chi, would be non-vanishing, okay, and eta would vanish, okay. And therefore we would interpret chi as the antiparticle degree of freedom. So instead of using psi in the Klein-Gordon equation, if you use eta and chi, then we would get a more interesting setup for the system, where you can identify eta to be the particle degree of freedom and chi to be the antiparticle degree of freedom, okay. And what we will do next time is to set up this equation in terms of eta and chi, and it has a form which is very close to the kind of form that you would see for Schrodinger equation. Okay, so I think I'll stop at this point. Any questions?
Sir, would you please send the slides?
Should I send the slides?
That would help.
Okay. Yeah, so I'll try to send the slides maybe later today.
Yeah, that's fine.
Yeah. So in fact, I could do it for the other courses also, in case people are fine with the. I also corrected that typo already. So where is it occurred, right? Yeah. So this is what I wanted to write. Rho n is equal to rho q. Okay. So I have a meeting to attend immediately. So of course, I think all of you also may be there. But maybe I'll try to send it by evening. But it's not like, I have too many. I mean, I pretty much used up whatever I have typed. So I'll have to type it up again for the next class. Okay. Is that fine?
Yeah.
So can I suggest one thing? Hello?
Yeah.
Yes, sir.
Can we have can we share a Dropbox folder?
Sure, I think we can.
I mean, I can send you an invitation. If you don't have Dropbox, you can kind of open Dropbox, this thing. And I'll put the file in the Dropbox so that, instead of cluttering emails with kind of, kilobytes, megabytes of files, we just put it in the Dropbox, and when it gets updated, the file gets replaced there.
Yeah, it's better. Be easier to find also later on.
Yeah, exactly. And that would kind of, otherwise, everybody Gmail will be cluttered with some, well, not idiotic, but like some bunch of things. Okay, so I'll try to do that maybe. Okay.
And also, if you get time, you could check out that feature, how to enable recording for others.
Yeah, absolutely. I mean, I do not want to kind of keep this kind of right only to me. Students pretty much have a right to record the stuff. And only thing is, I wish I knew how to do that. Yeah. Okay, maybe I'll just ask someone instead of wasting time trying
Yeah,
to. Okay. I mean, I would love to figure this out, but I don't think time is a luxury now, so I don't want to waste it.
sure.
Okay, any questions?
Sir, just an aside, I was curious. Do we derive this quantization of charge
Do we derive in what?
in
Are we going
some
to
other?
force? Is that the question, or is it possible to derive? What is the question?
Yeah, is it possible to derive, or do we just take it as
No.
an experiment?
Yeah. The thing is that, yeah. So quantization of charge actually doesn't come just like that. In fact, it is a consequence of having, say, magnetic charge. Okay. So there is something called a Dirac quantization condition for charges, and that tells you that the electric charge is quantized uh, provided if there exists a magnetic monopole charge. Okay, so if there's a magnetic monopole charge, it will tell you why electric charges are quantized. But if there is no magnetic monopole, so far we have not seen magnetic monopoles in the nature. A lot of experiments have been done, and there is no positive result at all. So in the absence of that, it is not so easy to explain as to why charges are quantized actually. Okay. But
Okay.
if you have magnetic monopole, then there is a very simple, very, very, very natural way of explaining as to why charges should be quantized. Maybe some other time, but not in this course.
Also, sir, in the same framework, Dirac talk about his sea of electrons, holes.
Yes.
He says that all the negative energy states are filled.
Yeah.
Yeah, but in that argument, aren't we violating this charge conservation, because this all the states, negative energy states, being filled with holes?
No, you are not. I mean, that is how the initial interpretation was. But you don't need to kind of subscribe to that way of interpreting it. All you need to say is that to occupy a negative energy state, you still need to kind of pump in a positive energy, basically. So to put it a little differently, if you want to produce an electron and a positron, okay, electron has mass 511 keV. So to produce electron positron pair, you minimally need energy which is twice as much of that. Okay, so therefore, even if you want to create a hole in what is called the Dirac sea, you need to pump in a positive energy. Okay.
Yeah.
So initial interpretation was like that all negative energy states are filled up, but you don't need to interpret it that way anymore.
Okay.
Okay, so can we close the session?
Yeah, I think.
Okay, I'll stop recording.